So, good afternoon. My name is Saurabh Kadekodi. I am a research scientist at Google. I work with the storage analytics team, and I'm here to talk about some work that I have done called DARE, or Disk Adaptive Redundancy. And the whole title is Tailoring Data Redundancy to Disk Reliability Heterogeneity in Cluster Storage Systems. So the title is a mouthful, and as I go along the talk, I'll explain. This was work primarily done when I was a PhD student at Carnegie Mellon. I was then a collaborator with Google, hence not the Google logo, but the CMU logos. So in this talk, I'm going to go through some background and motivation, followed by some disk failure rate heterogeneity collected in the field, then making a case for disk adaptive redundancy, then showing how we can overcome something called transition overload of changing redundancy schemes, evaluation on some real-world cluster traces, and finally the newest work, which is about overcoming placement restrictions that are posed by other disk adaptive redundancy systems, and finally a small, very brief look at how we can incorporate this in a real system like HDFS. Okay. So to start, today's storage clusters look, basically this is the toy diagram, and in reality looks something like this. So cluster storage systems are nothing but the storage subsystems of large distributed systems. They contain thousands to millions of hard disk drives in their primary storage tier. And at such scales, failures are extremely common. And failures typically are measured using a metric called annualized failure rate, or AFR, which is nothing but the expected percentage of disk failures in a given year. Now, the most common way to protect against data loss is via data redundancy. So you could have that either in the form of replication or in the form of erasure coding. And a cluster can have both being done simultaneously. So before we go ahead, let me give a small primer on erasure coding. So erasure coding is the more space-efficient alternative of replication. Typically denoted as a K of n scheme. It has K data chunks and n minus K parity chunks to form an n chunk stripe. All of these chunks are typically of the same size, a few megabytes. And whenever a chunk fails, you can use any K of the remaining chunks in order to reconstruct that failed data. The overhead is calculated as the ratio n over k, and reliability typically is proportional to the storage overhead. So in this example, I have a 3 of 5 erasure code, which has an overhead of 1.66, and a 6 of 9 erasure code, which has an overhead of 1.5. And as you can expect, the 3 of 5 code is more reliable compared to the 6 of 9 code. So bulk of the data in today's large-scale storage clusters is erasure encoded, because that is more space efficient and therefore cost efficient. Now, data is growing at an alarming rate. I don't need to tell this to this crowd especially. This is a plot shown by Eric Brewer, which shows YouTube data growing linearly on a log plot, which means it is actually growing exponentially. We saw Google Photos changing their policy to now allow only 15 gigabytes of storage because of the unbelievable number of photo uploads that happen every day. And there was also an IDC document that talked about how the data is increasing, potentially reaching to 175 zettabytes by 2025. And even then, 80% of the bytes are expected to reside on hard disk drives. So at such scales, even single-digit percentage improvements in storage efficiency amount to massive savings of over millions, potentially even billions of dollars. And this talk that I'm giving today is about saving something like 20% storage space by applying disk adaptive redundancy. Okay, so let's go into the technical details. The current assumption in a storage cluster is that all disks fail similarly. So multiple redundancy schemes may be used in the entire fleet, but these redundancy schemes are unaware of the AFR differences of the different disks in the fleet. With this, I'm going to now talk about the actual disk failure rate heterogeneity that we measured in the field. So that even though the toy diagram shows that all disks look similar, in reality, it's something like this, where you have disks of multiple makes and models installed within a single storage cluster. In this example, we have 3 makes and models, where the green disks are the most reliable, followed by the blue disks, and finally the yellow disks are the least reliable. So when you have the same redundancy scheme in this cluster, they actually may provide different reliability because the disks on which they are stored, the chunks are stored, are not failing at the same rate. So in this example, the top stripe is less reliable compared to the bottom stripe because the top stripe has many more chunks on the yellow disks, which are the risky disks. So same level of redundancy is either insufficient or wasteful, but given that storage administrators typically are paranoid about data loss, it is mostly the latter. So you have excess redundancy, which is modeled according to the worst failing disk, and you have those many copies for all disks, which makes it excessively wasteful. Now, here is a box and whiskers plot of the AFR data that we collected in the field from over 5.3 million disks across 60 makes and models in 3 large deployments of NetApp, Google, and Backblaze. So here, the x-axis, each box corresponds to one single make model having at least 10,000 disks. And the y-axis is the AFR on a log scale, and the black dash is the median of the AFRs of that population. So we can see that the difference between the weakest and the strongest disks in terms of make model segregation is at least 100x. Okay, so not only does AFR vary across disk makes and models, but it also varies across a disk's lifetime. To show that, I use the disk hazard curve or the bathtub curve, which has the age of the disk on the x-axis and the AFR on the y-axis. The starting of the bathtub curve is when disks face a high failure rate in terms of infancy or infant mortality. This is followed by a low stable failure rate regime via useful life. And finally, we have the high failure rate wear out. So failure rate also varies across a disk's lifetime. Now, when default redundancy, suppose a single redundancy scheme is used throughout a disk's life, its configuration is set to something that has been observed as the worst failing disk across any part of its lifetime in the cluster. So typically, if you have a bathtub curve and the gray region is showing you the protection provided by the redundancy scheme, you can assume that the entire failure curve is well within the protection level of the redundancy scheme. Essentially here, our default is used throughout all disks throughout their lifetime. Now, the concept of disk adaptive redundancy is to identify this low failure rate regime of useful life and then remove excess redundancy by tailoring the data redundancy to the observed AFR. When you have lower redundancy in response to lower failure rate, you have lower storage overhead and therefore lower storage cost. Okay. So there are many challenges in building a disk adaptive redundancy system, and I'm going to go through them now. One is that you have to monitor these AFRs in the field and on the fly. If you look at all the spec sheets, all disks do actually fail similarly. But in reality, in a production environment, they respond differently to different kinds of workloads or temperature or vibration patterns and so on. A disk adaptive redundancy system has to handle AFR heterogeneity across makes and models and across device ages. So the goals of a disk adaptive redundancy system are, first and foremost, keep all the data safe throughout the disk's lifetime. Second, be accurate in the measurement of when to change redundancy, because if you're not very accurate, you might change redundancy when the failure rate is still high, and that can lead to data loss. All of these mechanisms of redundancy tuning have to happen in an online fashion. So if you look at the entire bathtub curve and then realize at a later point that I could have changed my redundancy in the past, that opportunity is lost. And finally, all of redundancy tailoring operations are essentially background operations. So they must happen efficiently without interfering with the foreground traffic or causing minimal interference. And the benefits of disk adaptive redundancy is safer redundancy, because now you have a system that is nimble enough to actually adapt to the redundancy changes that are happening, so the failure rate changes that are happening. And in terms of monetary benefit, it is cost effective because you have adequate protection and not excessive protection for your data. Okay, so here I have two makes and models and their timelines. As the disks go through their ages, they develop a certain bathtub curve, and originally you would have used the R default throughout both disks' entire lifetime. So when you have multiple makes and models, we want to only keep the default redundancy during the high AFR phases of infancy and wear out, and have a tailored redundancy, efficient redundancy for each make model during its useful life. In this case, Rx and Ry. So I'm going to, R specialized is defined according to each make model's useful life. Now I'm going to abstract this timeline, and we're going to ask a bunch of questions about this timeline, which will help us develop our disk adaptive redundancy system. So given this timeline of R default at the ends of the disk's lifetime and a specialized redundancy scheme in between, first we want to ask the question of when should disks transition. Second is what schemes should disks transition to. There are more questions that will come later in the talk, but primarily let's focus on these two questions. So this is where we come to making the case for disk adaptive redundancy. And so the first disk adaptive redundancy system we envisioned is called Heterogeneity Aware Redundancy Tuner, or HART. It takes two inputs, a mean time to data loss target, that is the target reliability you want all your data to always have, and the continuously captured disk monitoring data. HART consists of three components: a change point detector, an anomaly detector, and a redundancy tuner. I'm going to describe these components in a bit. And just to let you know, HART, it was a paper published in FAST 2019, where you can get all the details of the work. So coming back to our timeline, when should disks transition? Basically, what we're asking is, how do we detect that the AFR has changed? And for that, we use the change point detection mechanism. So why is it important to know when should disks transition? So data can actually be under-reliable if end of infancy is declared too early, or the onset of wear out is declared too late, because the AFR curve is high during those two regimes of life. HART uses an off-the-shelf change point detector to identify the different knees of the curve. And as soon as the change point detector has statistically accurately identified that a change point has happened, it will inform the system to lower the redundancy to the observed failure rate. Now, an important thing to realize here is that the infancy to useful life change point can be decided, as in the transition can happen slowly, since your failure rate is actually reducing. So none of your data is at threat. But the opposite transition of useful life to wear out has to happen urgently, because your failure rate is climbing. And so you want to make sure that you're not under-reliable in that regime. Second is, all of these in-the-field statistics have a lot of noise in them. So how do we trust the observed curve, AFR curve? And for that, we use an off-the-shelf anomaly detector that can allow us to identify spikes in failures, which would potentially be because of certain correlated failures, or which are extraneous to the make model itself. For example, if an earthquake happens and knocks down half the racks, that is not something that we would attribute to the bathtub curve of a make model. And so we want to remove that data from the failure curve and only look at failures that happen because of that happen in the normal operating conditions of the cluster. So the details of the anomaly detector are in the paper. Now, coming to the next question, what schemes should disks transition to? Essentially, what requirements should these schemes fulfill? And for that, we have the redundancy tuner. And in HART, we follow a constraint-based selection of schemes. So you have the observed life AFR as one of the inputs to HART. And now we have a bunch of constraints encoded in HART, which we have designed based on speaking to storage administrators of large clusters. One is the target MTTDL you want to achieve, the mean time to data loss, the target reliability. Second is the maximum reconstruction I/O you are ready to tolerate in case of a failure. Along with that, there are other such constraints like the minimum number of failures that you would like to have based on the architecture of your data center, the maximum code width of your Erasure code that you're willing to support, and maximum repair time, and so on. So you have all these constraints. And now, when you have an AFR, you filter the available schemes that you want to use through all these constraints, and now you have a subset of schemes that you are left with. From among those, you sort them by increased space efficiency or lower space overhead, and use that as the specialized scheme for that make model in that make model's useful life. Okay? So HART provides huge benefits. It was evaluated on storage cluster traces of clusters with over 100,000 disks. It promised substantial space savings over one scheme fits all redundancy, which is what is practiced today, up to 33% lesser space compared to three-way replication, and 11 to 16% lesser space compared to popular Erasure codes such as 6 of 9 or 10 of 14. Just to remind the audience that any savings above 10% are tens of thousands of fewer disks, which means millions of dollars in saved cost. Not to mention that it also causes lower operational cost in terms of potentially lower carbon footprint. Now, HART is great. It provides all these benefits. However, there is a problem. HART suffers from something called transition overload. So what is transition overload? So given your bathtub curve and the two transitions that I explained, end of infancy and start of wear out, they both don't come for free. You have to have an I/O cost associated with changing redundancy from one scheme to the other. Secondly, as I mentioned before, the transitions from useful life to wear out are urgent transitions that you cannot postpone. Yes? So both these things together, high I/O cost and urgent transitions, make up something that we call transition overload. And now we will talk about our improvement over HART, which overcomes transition overload. So we looked at HART on large, over 100,000, in fact, between 300 to 500,000 disk clusters at Google. And I'm going to show plots like these. Let me explain those plots. So on this plot, we have the date on the x-axis. The very left is the birth of the cluster, and on the right y-axis, what you see is the increase in the disk population of the cluster over time. Okay? The same x-axis on the bottom graph with the left y-axis is showing the amount of I/O bandwidth used to perform redundancy changes whenever they were warranted in this particular cluster's deployment. So I'm going to overlap these graphs like this. And what this shows is that if you look at 2019, do you see my cursor? Actually, you don't. Okay. If you look at 2019 August or near 2019 September, so 2019 September, about weeks at end, more than 100% of the cluster bandwidth was used in performing redundancy transitions for disk adaptive redundancy. Now that clearly is not okay, because the primary job of the cluster is not to change redundancy, it is to service user reads and writes. This happened because too many disks were transitioning together from one phase of life into another. And this is not just an artifact of this one cluster, but also showed up in the other clusters that we looked at. And so we developed Pacemaker, which does the job of efficiently regulating the heart. Pacemaker was published in OSTI 2020. It also has 3 components: a proactive transition initiator, a redundancy planner, and an efficient transition executor. I'm going to explain these 3 components as well. So coming back to our timeline, we answered how should we decide when to change, what schemes to transition to, and in the first question, we add a third sub-question, which is, when can we start transitioning before it's too late, so that we can throttle our transitioning and do it safely. And for that, we use the proactive transition initiator. So before we go into the details of how we do it, we observe two interesting disk deployment patterns that are going to govern how our proactive transitions are going to work. So the first is something that we call trickle deployments, where you see this cluster where disks are deployed few at a time, but regularly, causing a gradual increase in the disk population. This is in contrast to other kinds of clusters we looked at, where disks were deployed in tens of thousands of disks within a very short span of time, which we call step deployments. We are going to see that Pacemaker has different solutions based on whether the deployment pattern is trickle or step. Okay, so let's look at what happens with a trickle deployment and when we want to understand the AFR. So in this video, what you're seeing is at the bottom, you're seeing the bottom rectangle, you're seeing the disk population slowly growing over time. And in the top square, what you're seeing is the AFR curve of that disk population as the disks are being trickled in. Remember, AFR is a population statistic. So as the disk population goes on becoming higher, you get a higher confidence on the AFR. So the leading edge of the AFR that is being formed is in fact very jittery, but as you look at towards the left of the curve, that is much more stable because now it is dependent on a much higher population. The AFR estimate is based on a higher population. Now we take, by virtue of this AFR behavior, what we do is for trickle deployments, we identify a leading period where the disks in that period are called canary disks. And Pacemaker marks the first C disks as canary disks. And it does not transition the redundancy for those disks, but only learns the AFR curve from those disks, and then applies that knowledge to the bulk of the disks that follow the canaries. So the remaining disks now have a full picture of of the bathtub curve, which allows them to proactively start their transitions whenever the bathtub curve's rising edge is observed, rising level is observed. So canaries can help in proactively transitioning trickle deployed disks. But now, this same logic cannot be used for step deployments because most of the disks are deployed of the same make model are deployed together. So if we are going to treat everything deployed in the first 2 weeks or a month as canaries, for step deployment, we'll end up marking everything as canaries. And then we'll have no opportunity to transition the redundancy. Instead, we leverage the fact that a lot of disks are deployed together, which gives us a high confidence AFR from the get-go. So here you see a huge population of disks deployed in a very short span of time. Even the leading edge of the AFR curve that you see is not as jittery as the trickle deployed disks and is much more stable. So we can rely on the fact that lots of disks have been deployed together and in fact use that AFR curve directly to help us understand when to transition. So from here we get a high confidence AFR. And another important observation allows us to build an early warning system to proactively transition our disks. The other observation is that disk AFRs grow gradually. So you don't see a sudden increase as is seen in the toy example of disk AFR suddenly going up in wear out, but they gradually increase in the wear out over time. And so the high confidence AFR plus gradually rising AFR allows us to have these watermarks that we can set when they're crossed, you can start transitioning disks before the redundancy level is too low for the observed AFR. Okay, let me just check time. Okay. So now we answered when should disks transition and what scheme should disks transition to. But now there's a third question, which is how should the disks transition? So can the transition IO itself be reduced? And for that, we have the efficient transition executor. So now suppose we want to change a redundancy scheme from a K1 of N1 into a K2 of N2 scheme. In the most naive sense, what we would do is read, re-encode, write, which is if a disk changes failure families, you would need to read all the chunks of the stripe on other disks, write them to the new disks, recalculate their parities, and remove the older stripe. Now this requires an I/O which is 2 times K1 times the disk capacity. The equations are not important. The point is lots of I/O. Now the transition executor leverages the different deployment patterns and allows us to find two efficient techniques to perform transitioning. In trickle deployment, in steady state, we can expect that because disks are being deployed a few at a time, they will enter any regime of life a few at a time, and also will leave only a few at a time. And so whenever a disk is about to depart, we can simply move the data onto a newly arrived disk, reconfigure the metadata, and transition an empty disk. And so the cost of moving is much cheaper than the cost of read, re-encode, write. And you still have adequate protection for your data. Now, when you have step deployments, all of the disks are deployed together, meaning they will all transition together. So you cannot move all of that data somewhere. Instead, what happens is, because all the disks change their regime of life together, you don't have to move data. You can simply recalculate your parities based on different number of data chunks without any data movement, and you get a new scheme without having to do any additional data movement or very little movement, which is required just to form the new stripes. So bulk parity recalculation saves n1 times the cost of read, re-encode, write. In this way, transition executor allows us to reduce the transitioning cost itself. Now, as I said before, I showed you the toy bathtub curve and spoke about how the AFR curve doesn't really increase suddenly at wear out. And these are some of the bathtub curves that we observed in practice, which is consistent with our observation. So first, some more observations from practical bathtub curves are that useful life isn't really flat. In fact, if you look at this useful life, it is gradually increasing over its lifetime instead of being completely flat. So now we revise our disk bathtub curve understanding, and instead of having this curve, what we're saying is the real bathtub curve looks something like this. Okay? What this does is, you have your regular clusters that do not do any disk adaptive redundancy, but now you have this modified disk adaptive redundancy cluster that may require multiple phases of useful life, not just a single one. Because if you only have one useful life phase, that phase might be very short because your bathtub curve is increasing even in useful life. Now for each of these phases, you need to perform re-encoding, and all of the increase in redundancy operations are in fact urgent operations. So Pacemaker is designed to also do multiple phases of useful life, not just a single one. So now again our timeline gets revised with multiple specialized redundancy schemes for a disk's lifetime, again having those 3 questions. And now so having multiple phases means multiple transitions, and you want to make sure that you're not overwhelming the I/O of your system by doing a lot of transitions many times. And so for that, we have a modification in our constraint-based approach for transitioning. So we have our original constraints that Hart specified, but now we also have 2 I/O-based constraints that help us choose which scheme to transition to. The first is the average I/O constraint. So we would like to throttle the amount of average I/O that is performed for the entire disk's lifetime on redundancy transitions. Suppose you can afford to spend 1% of the average I/O towards redundancy transitions. That would be our average I/O constraint. And the peak I/O constraint would be the amount of I/O bandwidth you're willing to use whenever you have to transition, the max, which is at any point you don't want to go above this I/O. So using the average I/O constraint and peak I/O constraint, you can now have a scheme selection, or you can choose to have fewer phases of useful life if required. For example, if you realize that you have if you have transitioned too many times in quick succession across too many phases of useful life, the next scheme you use can be a very conservative one, because now you have spent a lot of I/O already on transitions. And the opposite example is that if you have had one long phase of useful life, you can afford to have more smaller phases of useful life until you are safely below your average I/O constraint. Okay. So now let's look at some evaluation on real world failure cases. So here we have that horrible transition overload example from one of the disk clusters at Google. And now with our redundancy planner, efficient transition executor, we completely slash all of the I/O, and all of the I/O is safely below 0.3% of the cluster's I/O bandwidth on average. So you only need 0.3% in order to perform all the redundancy transitions across various phases of useful life for each disk. And the peak I/O in this case was always under 5%. So this is a detailed diagram of the different transitions that are happening throughout the cluster's lifetime. So the dark gray patch are the disks that are spending their time in infancy in default redundancy. The light gray is just the growing total population. And the blue patches that you see are the I/O patches that are due to redundancy transitions that are happening because of Pacemaker. And red is just the reconstruction you have to do when you have failed disks. Now, the same x-axis on the bottom graph shows you the space savings that were possible because of Pacemaker. So you have the 6 of 9 default redundancy scheme being used at the very beginning when all disks are in gray, dark gray. As the disks transition into more efficient phases of useful life, we can start using more efficient schemes such as 30 of 33, 10 of 13, 11 of 14, and so on, which always guarantee that your data is adequately safe, but you also have a lot of space savings. So here you observe an average space savings of 14% across the whole cluster's lifetime, peak savings at some points up to 25%, and in this cluster with over 350,000 disks, 25% savings is 75,000 fewer disks that you will need without sacrificing any reliability. So on other clusters too, we see similar space savings. So here are other two clusters where the top is showing you the transition overload and the middle figure is showing you the reduced I/O because of Pacemaker, and the bottom is showing the space savings. This is also true of a trickle deployed only cluster, which is Backblaze. Here you see a more finer mixture of schemes because of the way that disks trickle in, and they belong to many more makes and models compared to what we saw in Google clusters. Okay, so now a very quick view at how to enable disk adaptive redundancy in a real system like HDFS. This is going to be a really toy example, so but an insight nevertheless. So in HDFS, typically you have a name node that has a file manager, a block manager, and data node manager that manages all the data nodes. Now in Pacemaker, we essentially divide the fleet logically into disks having the same failure rate. And so in this way, we actually make copies of the data node manager, one for each failure family, and have only those disks talk to that data node manager. So whenever disks change failure rates going from infancy to useful life and so on, they can move from one data node manager into another, and all of their policies of redundancy, rebalancing, load balancing, whatever is taken care by that particular data node manager. By introducing this distinction at the data node manager level, the files and the blocks of HDFS remain unaffected. And you can transparently start using disk adaptive redundancy without the files or the clients or the metadata having to know anything about it at the file level. Okay, so this is all about disk adaptive redundancy using HART and Pacemaker. And very recently, we also introduced a new disk adaptive redundancy system called Tiger, which I'm going to talk briefly about, which is incidentally not in the slides that I uploaded. I added this very lately. So Pacemaker is really good in terms of the transition overload reduction, but Pacemaker also has certain problems. One is Pacemaker logically groups disks by similar failure rates. Yes. So stripes in Pacemaker have to be entirely stored within one failure rate, one group of disks having the same failure rate, right? So either a stripe resides in the blue disks or yellow disks or green disks. Now this poses a placement restriction, which is a very expensive thing in a large-scale storage cluster. Already, there are a lot of constraints that need to be fulfilled in order to place a stripe. No two chunks of the stripe can be on the same disk, or rack, or server, or power, for fault domain, etc. And adding one more constraint is potentially going to be crippling. So for that, we introduced Tiger, which is disk adaptive redundancy without placement constraints. And its two main components are something called eclectic stripes and eclectic volumes. Now, I'm not going to go into too much detail about this. This was published recently in OSTI 2022, and so I encourage you to go and take a look at the details of the paper. So just to differentiate between the different kinds of stripes, we have the homogeneous stripes, which are the conventional stripes, which assume the same AFR across the different disks. And therefore, two stripes are assumed to have the same reliability. In Pacemaker, you differentiate between disks of different makes and models or different failure rates, and you have two 6 of 9 stripes in different failure groups will in fact give different reliability, but this comes with a placement constraint. And eclectic stripes allow us to reason about the reliability of stripes by taking into account the differences in the failure rates of each of the individual disks combined in a stripe. And so we have developed a new way to calculate mean time to data loss that allows us to incorporate this AFR heterogeneity when calculating the MTTDL. So let's look at how the MTTDL looks like for the different kinds of striping mechanisms. So here on the x-axis I have the MTTDL values, and the black line is the target MTTDL that we want to achieve. To the left is when you are dangerously, so your reliability is below target, and on the right is when your reliability is above the target. And you always want all your stripes to be on the right, but as close to the black bar as possible, because the more you go to the right, the more wasteful it is. So in the original case where you assume the same reliability for all disks, and in fact you assume that all disks have the same average AFR, there is a chunk of stripes that are under-reliable, which do not meet your reliability target. So more often than not, operators assume the same reliability level to be the max AFR that is observed, which is when all your stripes are reliable, but they are in fact excessively reliable, which is costly. You have Pacemaker that creates redundancy groups and has stripes within those redundancy groups. So none of the stripes are under-reliable, but you still see clumps of stripes that are to the very right, which is and they're wasteful because they have a higher MTTDL than required. And with Tiger and eclectic stripes, you have all the stripes that are sufficiently reliable and in fact adequately reliable. They're closest to the black bar, and so you're not wasteful and you're always above the reliability target. Okay, so Tiger's conclusion is that Tiger provides disk adaptive redundancy without placement constraints using eclectic stripes and eclectic volumes. It provides up to 20% overall space savings, which is similar to what Pacemaker provided. It has very low overhead also, only requires 0.5% of the cluster's I/O bandwidth to do this. And it performs disk adaptive redundancy at the file or stripe level, which means your conventional redundancy mechanisms and Tiger's eclectic stripes can coexist in a cluster, which eases the adoption of disk adaptive redundancy. In Pacemaker, you have an all or nothing approach because it is at a disk-centric level. So the entire cluster has to commit to disk adaptive redundancy or none of them can do it. You cannot have partial adoption. But with Tiger, you can. So finally, disk adaptive redundancy is data-driven research based on looking at millions of disks in the fleet. It shows that there is a high AFR difference up to 10x even in the same cluster. And we have shown, we have made the case for disk adaptive redundancy to tailor redundancy to the observed failure rate heterogeneity, designed 3 systems that showcase the different ways in which to do disk adaptive redundancy, promising huge savings, and also showed proof of concept by building disk adaptive redundancy in HDFS. So that's all I have. Thank you. Any questions? Yeah.
Have you done any study on flash instead of rotating medium?
We have not. So we only looked at hard drives right now. The concept of adaptive redundancy is not limited to the device type. You could very well do it on flash. You could also do it at server level if you didn't want to do it at the disk level. The only problem is you have to have enough population to have statistically correct AFR measurements. So long as that is true, you can do it on any, but we have not tried on flash.
Also, you mentioned 2 types of cluster, right? Like one is trickle and other is step.
Yeah.
Do you have any case study like where it's a hybrid, where like the over life of a cluster, sometimes it's trickle, sometimes?
So in fact, the main diagram that I showed.
Can you repeat the questions or summarize it or something?
Sure. So yeah. So the question was, I showed trickle deployed clusters and step deployed clusters. Is there a hybrid of trickle plus step that happened? The main cluster example that I showed, in fact, was a trickle plus step example. So this, let me show you. Yeah, this particular cluster that I showed had both trickle deployment plus step deployment in its lifetime. Sorry, one second. He had a question. I'll just answer his first. Yes.
Oh yeah. Was there smart metrics that you looked at that predicted the early wear out, like reallocated sectors growing fast or increase in AFRs?
So that's a really good question. We currently have so the question is, did we look at smart metrics of the disk to understand early failure probability? And we did not. That's a really good question. We currently only looked at age as the x-axis of our bathtub curve. You can very well imagine it to be much richer combination of other things that we know cause disks to fail sooner, and you can take a look at it. But for this study, it was only age-based. Yes?
So why is this only a POC and not an actual deployment?
So the question is, why is this only a proof of concept? It's because, one, I did it when I was a student. I did not have the clout to influence someone to actually build it. Two, changing something like the redundancy settings in a very large scale system means that I have to convince people who are generally very paranoid to be less paranoid, even though I'm telling them you have to reduce redundancy. When I make statements like this, people are like, no, reduce redundancy, that's not okay. But I'm trying to make a case to prove to them that it's safe to do so. And so hopefully it will see the light of day soon based on the promising numbers of this POC.
There was 5.3 million drives in the POC.
So are there 5.3 million drives in the POC was the question. No, the failure characteristics were looked for from the 5.3 million drives, but the 4 clusters that we looked at in the POC together have over 1.6 million drives in them.
Last one, did you have a meantime data loss or durability target? You never mentioned it.
The question was, did we have a mean time to data loss target? And yes. So we assumed that if you have 6 of 9 as your erasure code, whatever was the maximum failure rate that you observed across all the 5.3 million drives, and if you use 6 of 9 for that failure rate, we assume that that is something you could tolerate. So that is our mean time to data loss target. Yes?
So when you reduce redundancy, right, what is the target erasure code? How do you come up with that? Like, which target erasure code you can go to?
So the question was, how do we choose the target erasure code to convert to when we are reducing redundancy? So there is a set of schemes we can choose from. And those schemes are generally dictated by the architecture of the storage cluster and the different policies that are being used by any distributed system in that cluster. And so the administrators typically say you can use either this encoding or that encoding or whatever, and they have a set. So from among those sets, we choose the ones that fit our constraint criteria of, does it have enough number of minimum failures? Does it meet the target MTTDL? Does it have low enough reconstruction cost? And so on, to select the target. Any other questions?
And I assume you want to only have a limited number of K of n.
So the question was, do we only want to have a limited number of K of n? In reality, we do end up having a limited number of K of n. So one of the things that is really a bottleneck in having wide K of n's is that you want to have enough fault domains to be able to place your data. And that becomes the bottleneck. And so most often than not, that dictates what is the widest you can have, which is not terribly wide, and which is why you often have only a handful to choose from.
But with Tiger, you could have really hard.
Yes. So with Tiger, we can have many, many more combinations of things we can do. Yes.
So I believe I saw a 30 of 33.
Yes.
Is that actually something that's used in production? Is that just for the POC?
So the question is something like 30 of 33 actually used in production? I cannot comment on what is used in production. I can say for sure that that is not unreasonable. Backblaze has already reported using 17 of 20. Yeah.
If they're using 6 of 9, I'm sure 30 of 33 makes them very uncomfortable.
So yes, 30 of 33 does make people uncomfortable, including the reviewers of our paper. But we are trying hard to convince them that it is not unreasonable. But let's see. Okay. Yes.
What's next?
What is next? So one of the things we are looking at is looking at a more structured way to predict failures, so that we can have a finer control over when things are going to fail. That is one of the things we're looking at. And the other things that I am looking at are unrelated to this. Yeah. Okay. Thank you.